All right, so we're diving into a theory today that says gravity might not be a pull, but a push.
Yeah.
I know, right? Wild stuff.
It's
called the Grand Fibonacci SMF RVS theory of gravity, and it's really turning everything we thought we knew about the universe upside down.
Yeah, it's a fascinating concept.
Yeah.
It suggests that instead of mass attracting mass, objects are actually being pushed by something called pressure gradients in the vacuum of space.
Pressure gradients.
Yeah.
Vacuum of space.
Yeah, okay.
I think that's where I start to get a little lost.
Okay.
I thought space was, well, empty.
Well, it's not as empty as we once thought.
Ah.
This theory proposes that the vacuum of space has a structure and varying pressure.
Okay.
Almost like an ocean with different densities.
Okay.
Imagine a cosmic ocean
Okay.
with currents and eddies pushing objects around. That's kind of what we're talking about here.
So instead of Earth pulling me down with its gravity, I'm actually being pushed down by something in space.
Exactly.
I'm trying to picture this.
Yeah, and this push is thought to be created by the interplay of two key components: subtle magnetic fields, or SMFs,
Okay.
and the relative vacuum of space, or RVS.
Okay, SMS and RVS, got it.
Yeah, think of SMS as a kind of cosmic web connecting everything in the universe.
Okay, cosmic web, I got it.
Yeah.
But how do these SMFs and the vacuum of space work together to create this push?
Well, imagine you have a bathtub full of water,
Okay.
and you create ripples at one end.
Uh-huh.
Those ripples create variations in the water pressure,
Okay.
and they can cause a rubber ducky at the other end to move.
So the SMFs are like the ripples.
Yes.
And the RVS is like the water in the bathtub.
That's a great analogy. The SMFs create these variations in the pressure of the RVS.
Okay.
And those pressure gradients are what push objects around, creating what we perceive as gravity.
Okay, that actually makes sense. So it's not about mass attracting mass, it's about these pressure differences in the vacuum of space pushing things around.
Right.
But hold on. What about all those years we spent learning about Newton and Einstein?
Yeah.
Were they wrong about gravity?
Not necessarily. Each theory builds on the previous one.
Okay.
Newton gave us a way to calculate gravitational force, and Einstein revolutionized our understanding with his theory of curved space-time.
Right.
But there were some things they couldn't fully explain, like why galaxies rotate the way they do, or why the universe is expanding at an accelerating rate.
So those unexplained phenomena are where this new SMF-RVS theory comes in. It's like trying to solve a puzzle where a few pieces are missing.
Exactly.
And this theory provides those missing pieces.
Exactly. And it does so by offering a different framework for understanding gravity, one based on these field interactions, rather than the traditional idea of mass attraction.
Okay. So this is a pretty radical shift in thinking. And you mentioned that it explains some of the things that Einstein and Newton couldn't.
Yes.
Can you give us some examples?
Absolutely. One of the biggest mysteries in astrophysics is why galaxies rotate the way they do.
Okay.
The stars on the outer edges of galaxies are moving much faster than they should be if gravity were solely based on the visible matter. To explain this discrepancy, scientists came up with the idea of dark matter.
Right, dark matter.
This invisible substance that supposedly makes up most of the universe's mass.
Right, I've heard of that, but it's always sounded a bit like a fudge factor to make the equations work.
That's one way to look at it.
Yeah.
But the SMF-RVS theory offers a different explanation. It suggests that those fast-spinning galaxies are actually being pushed outward by these pressure gradients in the RVS.
Okay.
The stars are being pushed, not held together by some unseen force.
So no more need for dark matter. That's pretty mind-blowing.
It is a different way of thinking about it.
Yeah, what about other phenomena? Does this theory explain things like black holes and gravitational lensing?
It does. Instead of black holes being these infinitely dense singularities that warp space-time, the SMF-RVS theory proposes that they are regions of extremely high pressure in the RVS.
Okay, so instead of a hole in space-time, it's more like a peak in the cosmic ocean.
Exactly.
Okay.
And as for gravitational lensing, the bending of light around massive objects, the theory says that this happens because the pressure differentials in the RVS create a kind of lens that bends the light, much like a glass lens does.
So we're literally seeing the universe in a whole new light.
Yes.
All thanks to this new way of thinking about gravity. This is really amazing stuff.
It is.
But I know there's a mathematical equation involved, too.
Yes.
And that's where my head starts to spin.
Yeah. The theory is represented by a new equation that incorporates some advanced mathematical concepts.
Okay.
Including something called the Fibonacci function and fractal scaling.
Okay. I have to admit,
Sure.
math is not my forte.
I understand.
But can you give us a simplified explanation of what this equation is all about?
Sure.
What's the key takeaway for us non-mathematicians?
The key thing to remember is that this equation replaces the concept of mass as the primary source of gravity with the interaction between the SMFs and the RVS. Instead of gravity being determined solely by how much mass an object has. It's about how this object interacts with these cosmic fields.
So it's not just about how big something is,
right,
but about how it fits into this cosmic web of SMFs and the RVS.
Precisely. And this equation also incorporates the idea of fractal scaling.
Okay.
Which suggests that the universe might be structured in a fundamentally different way than we currently think.
Fractals, that's like those repeating patterns you see in nature.
Yes.
Like snowflakes and coastlines.
Exactly.
But how does that apply to the entire universe?
Well, imagine a coastline.
Right.
If you measure it on a map, you get one length. But if you zoom in and measure every cove and inlet, the length increases. And if you keep zooming in, the length keeps increasing, even though it's still the same coastline.
So the closer you look, the more complex it gets.
Yes. And the SMF-RVS theory proposes that the universe itself is structured in a similar way. The interaction between the SMFs and the RVS creates these repeating patterns at different scales, which ultimately influence the push of gravity.
Because it's like the universe is this giant, infinitely complex fractal, and gravity is a reflection of that underlying structure.
Exactly.
That's pretty mind-blowing.
It is a fascinating concept, and it allows the theory to potentially explain a lot of the things we observe in the universe without needing concepts like dark matter and dark energy.
All right, we've covered a lot of ground here, from cosmic bathtubs to fractal universes.
We have.
But before we get too far ahead of ourselves, let me just check in with you, dear listener. Are you following all of this? Because this is some pretty revolutionary stuff we're talking about here.
It really is. And the implications of this theory, if it proves to be true, are incredibly far-reaching.
Well, that's a perfect segue to the next part of our deep dive. We've laid the foundation.
Okay.
But now it's time to explore the mind-blowing possibilities of this new theory of gravity.
All right.
What could it mean for our understanding of the universe, for space travel, for the very nature of reality itself?
Yeah.
We'll tackle all of that when we come back.
Sounds good.
All right, we're back and ready to explore the implications of this mind-bending theory. I mean, if gravity's a push and not a pull, does that mean we could potentially control it?
That's one of the most exciting possibilities. If we could understand how these SMFs and the RVS interact, we might be able to manipulate those pressure gradients.
So instead of fighting against gravity, we could potentially work with it. Like imagine spaceships surfing these cosmic waves you described earlier.
Precisely. Instead of relying on rockets and brute force, we could potentially navigate space by harnessing these natural pressure gradients.
That sounds like something straight out of science fiction.
It does.
But wouldn't that require a whole new level of technology? I mean, we're talking about manipulating the very fabric of space here.
It would certainly be a technological leap, but the potential rewards are enormous. Imagine the possibilities for space exploration if we could travel to distant stars without the limitations of traditional propulsion systems.
It would be a game changer. We could explore the universe in ways we've only dreamed of. But wouldn't that be incredibly dangerous? What if we accidentally disrupted these pressure gradients? Could we create some kind of cosmic catastrophe?
That's a valid concern. Any technology that powerful carries inherent risks.
Yeah.
But I believe that with careful research and responsible development, we can mitigate those risks.
Okay. I'm trying to wrap my head around all of this.
Yeah.
So we could potentially travel faster, farther, and more efficiently.
Yes.
But what about other applications? Could we use this understanding of gravity to create new technologies here on Earth?
Absolutely. Imagine being able to manipulate gravity to create new forms of energy generation, transportation, or even construction. We could build structures that defy our current understanding of architecture.
So we could have buildings floating in midair.
Potentially.
Or vehicles that hover above the ground. I feel like we're entering a whole new realm of possibilities.
It's certainly a realm ripe with potential.
Yeah.
And it's not just about the practical applications. The SMF-RVS theory also has profound implications for our understanding of the universe as a whole.
Okay, let's talk about that. How does this theory change our view of the universe?
Well, if the universe is structured as a giant fractal, as the theory suggests,
Uh,
it implies a level of interconnectedness we haven't fully grasped. The patterns governing galaxies could also apply to the smallest particles.
so it's like a giant cosmic tapestry with every thread connected to every other thread.
Exactly.
Even the smallest actions could have ripple effects across the entire universe.
Exactly. It challenges our perception of separation and highlights the intricate web of relationships that bind everything together.
That's a pretty profound thought. It makes you feel both insignificant and incredibly connected at the same time. But if everything is connected, does that mean there's some kind of cosmic consciousness? Like a universal mind? Are we getting a little too woo-woo here?
It's certainly a question that arises from this idea of interconnectedness.
Yeah.
If the universe is this complex, self-organizing system, could there be some form of awareness or intelligence at play?
That's a big question.
It is.
And one that might be beyond the realm of science to answer. But it's certainly fun to speculate.
Absolutely. And even if we never definitively answer that question, the SMF-RVS theory compels us to think about the universe in a whole new way, to appreciate its complexity, and to question our assumptions about the nature of reality itself.
It's like this theory is not just about physics, it's about philosophy, metaphysics, the very essence of existence.
It certainly blurs the lines between those disciplines.
Right.
And it reminds us that science is not just about collecting data and crunching numbers. It's about exploring the mysteries of the universe and expanding our understanding of our place within it.
All right, listener, we've gone from manipulating gravity for space travel to contemplating a conscious universe.
Right.
But before we get carried away with all these mind-blowing possibilities, we need to address the elephant in the room.
You're right. As exciting as this theory is, it's important to acknowledge that it's still very new and faces a lot of scrutiny from the scientific community.
Well, that's understandable. Extraordinary claims require extraordinary evidence, right? So let's shift gears a bit and explore some of the criticisms and challenges facing the SMF-RVS theory. We'll dive into that right after this. Welcome back to the show where we're exploring this this grand Fibonacci SMF-RVS theory of gravity, the theory that's proposing some pretty radical ideas. But as we were just discussing, not everyone is on board with this new theory.
That's right.
Whenever you have a theory that challenges established paradigms, there's going to be skepticism, and for good reason. The scientific community is rightfully cautious about embracing new ideas without solid evidence.
So what are some of the main criticisms being leveled at this theory?
Well, one of the biggest hurdles is the lack of direct experimental verification.
Okay.
While the SMF-RVS theory offers elegant explanations for a lot of observed phenomena, we haven't actually detected these subtle magnetic fields or these variations in the vacuum of space.
So it's kind of like a beautiful puzzle where the pieces seem to fit, but we're missing a few key pieces to complete the picture.
That's a great way to put it. The theory makes sense on paper,
Right.
but we need concrete evidence to back it up.
Okay, so what kind of evidence would convince the skeptics? What are scientists looking for?
They're looking for a few things. First, they need to directly detect these SMFs.
Okay.
That would require developing highly sensitive instruments capable of measuring these subtle fields.
Second, they need to find evidence of these pressure gradients in the relative vacuum of space.
And how would you even go about measuring something like that?
It's a huge challenge. It might involve analyzing data from astronomical observations, looking for anomalies that can't be explained by current models of gravity. It could also involve conducting experiments in space, trying to create and measure these pressure gradients directly.
So there's still a lot of work to be done.
Yes.
It sounds like it could be a long road before this theory gains widespread acceptance.
Science is a patient process. Sometimes it takes decades, even centuries, for new ideas to be fully vetted and validated.
But wouldn't it be amazing if this theory turned out to be correct?
It would be.
I mean, we're talking about a fundamental shift in our understanding of the universe.
It would be a revolution in physics. It would change the way we think about everything from the smallest particles to the largest structures in the cosmos.
Okay, let's indulge in a bit of speculation for a moment.
Yeah.
Let's say hypothetically that this theory is proven right.
Okay.
What would be some of the biggest implications, not just for science, but for humanity as a whole?
Well, as we've discussed, It could revolutionize space travel.
Mm-hmm.
Imagine a future where we're not bound by the limitations of traditional propulsion systems,
Right.
where we can traverse the vast distances of space by harnessing these cosmic currents.
It would open up a whole new era of exploration and discovery.
Huh?
We could potentially reach distant stars and planets,
Hmm?
maybe even encounter other civilizations.
Yeah.
It's mind-boggling.
It is, and it goes beyond just space travel.
Yeah.
If we could control these pressure gradients, we could potentially manipulate gravity itself.
So all of those science fiction concepts like anti-gravity devices, flying cars, and levitating buildings
Potentially.
could become a reality.
It's not outside the realm of possibility.
Wow.
And think about the implications for energy generation. If we could tap into these cosmic forces,
Right.
we could potentially solve our energy crisis.
It sounds almost too good to be true.
It does.
But I guess that's the allure of scientific breakthroughs, isn't it?
Yeah.
They have the potential to change the world in ways we can't even imagine.
Exactly. And even if the SMF-RVS theory doesn't pan out in the end, the very act of exploring these ideas, of challenging our assumptions, and of pushing the boundaries of knowledge is invaluable.
That's a great point. Whether this particular theory is right or wrong, it forces us to think differently, to question what we thought we knew,
Yeah.
and to be open to new possibilities.
And who knows, maybe one of our listeners today will be inspired to pursue a career in science and make the next groundbreaking discovery that revolutionizes our understanding of the universe.
That's a great thought to leave our listeners with. So if you're out there and you're curious about the universe, if you're fascinated by the mysteries of gravity, or if you're just intrigued by the possibility of pushing the boundaries of human knowledge, we encourage you to dive deeper into this fascinating field. Who knows what wonders await us in the vast expanse of the cosmos?
The journey of scientific discovery is never ending, and there's always something new to learn. So keep asking questions, keep exploring, and keep an open mind.
And on that note, we wrap up our deep dive into the grand Fibonacci SMF-RVS theory of gravity. We hope you enjoyed the ride.